So the questions are going to be due this week, Taylor. So you're just a assignment ahead. No biggie. Luke.
For like worksheet 2, how do you put the alpha equation?
Sure. So yeah, so the alpha is always, so like say you have like cosine theta equals negative 0.52 or something. Alpha is going to be cosine inverse of the absolute value 0.52. So you need to be in radian mode. But that'll be...
I think I fixed that like halfway through, because I think I had it in degrees mode, and I was getting...
You're getting bonkers, gigantic answers. Yeah. Oh, that's... Figure that always happens, right? Just when you're ready to update, check something that like you kind of need to check, it's going to be easy to forget, and your calculator's... Do you guys have other questions about worksheets 1 and 2? Alyssa?
Can you do problem 3 on worksheet 2?
Certainly. Worksheet or problem 3, you say?
Yep.
Okay. So first thing we'll do is I'm going to draw a picture to kind of represent the interval that we're solving over. So 0, pi over 2, pi, 3 pi over 2. So we're looking at quadrants 2 and 3. And then using all silly turtles crawl, I know that tangent is negative only in quadrant 2. So there's my theta. So far, so good?
Yep.
Okay. The alpha always between the terminal side of theta and then the x-axis, the acute angle there. And then since the last axis I passed through was the vertical and theta is positive, I know that my equation is going to be theta equals pi minus alpha, where the alpha is going to be tan inverse of the absolute value, negative 5.25. And then it's calculator time. So I know that my mode is already in radian mode. I changed it earlier today, so I'm not going to check that, but you do want to be in radian mode to do this. And notice that I didn't type the absolute value in my calculator. I just dropped the negative sign when I typed it in. But I get 176 for this. And to check that, if you were so inclined, the tangent of that answer had best give me negative 5.25, which it does. And then 176 better be between pi over 2, which it's bigger than, and 3 pi over 2, which it's smaller than. So I am quite certain this answer is correct. Does that feel okay, Alyssa?
Yeah, and then when you do, when it gives you like the number theta number, when it's negative, would that mean that when you do your arrow, would it go clockwise?
Correct. So you want to do one of these like 7 or 8 or
yes,
one of these? Okay.
8, please.
Absolutely. So we'll start, again, we'll draw our picture. So 0, negative pi over 2, negative pi. Notice when I'm numbering these things, I'm also going clockwise, right? So we're talking about quadrants 3 and 4. Then we'll do all silly turtles crawl. I'll observe that cosine is negative only in quadrant 3, between 3 and 4. So there's my angle theta. So the alpha that we're going to draw in this case is here. Now, since theta is negative, and the last axis I passed was a vertical, I know I'm going to be adding theta. Again, remember or adding alphas, excuse me. That stuff all gets flip-flopped if we're doing a negative angle. So that's negative 2.24. So checking cosine of that had better give me negative 0.62, which it does. And that value has to be bigger than negative pi. Well, I know what negative pi is. It's negative 3.14. Certainly it's bigger than that, but still less than 0, which it is. So this one looks good as well. Alyssa, does that feel okay?
Yep.
Okay. Josie?
Can you do number 7?
Sure. So again, going around clockwise, so 0, negative pi over 2, negative pi, negative 3 pi over 2. So we're looking at quadrants, 2 and 3. Good with that? Okay. All silly turtles crawl. So sine is negative between quadrants 2 and 3. That happens in quadrant 3. So that's my theta. There's my alpha. So far, so good. Again, because the last axis we passed through was vertical, and because theta is negative, we're going to be adding alpha this time. Where alpha is sine inverse absolute value, negative 0.56. Again, when I type this into my calculator, I never type the absolute values. I just do that stuff in my head because, well, dropping a negative sign is pretty easy. So I have negative 255. So the last thing I'm going to check, so sine of that answer better give me negative 0.56, which it does. And that value is got to be bigger than 3 pi over 2, which it is, and has to be smaller than pi over 2, which it is. So we're good. Does that feel okay, Josie? Of course. So again, these ones with the negatives, same idea, right? We have to make a little modification, and remember geometrically that we're going the opposite way around when we're doing our rotations or whatever, but not too much more difficult, right? Still feels pretty similar. Melissa?
Just a question. So for like number 5, when the numbers are bigger than like the normal graph, for the when you do like theta equals the number like minus the other one, do you just do the x that you pass?
Yeah, so usually I don't bother with the verticals on something like this, like, 0, pi, 2 pi, 3 pi, etc. So I know I'm going to be at 11 pi, and then 12 pi. I can see right away that the odds are on one side, the evens are at the other.
Yep.
So that's certainly enough.
So what would be like the problem?
Okay.
What number would you use?
Sure. So all silly turtles crawl. Cosine is positive in quadrant 4. So there's 2 pi, 4 pi, 6 pi, 8 pi, 10 pi. There's that. There's my alpha. Since the last axis we passed was vertical and we're positive this time, we're going to be subtracting. So theta is going to be 12 pi minus alpha, where alpha is cosine inverse of absolute value 0.19. Yep. So Alyssa, this number here is always the end of the x-axis that we're using to make our alpha.
Because in your key.
Yeah. So I did some
Yeah, you subtracted by
Probably what I did is I subtracted 10 pi off of
yeah.
the interval to just make it between
Okay.
1 pi and 2 pi, which is the same position, and then just added 10 pi back again at the very end,
Okay.
which is fine to do also. I stopped doing that some years ago because it felt confusing for students rather than just drawing the picture and just using everything from the picture. But either way, either way of doing it, it's really the same process. It's just like how you want to show your work.
Okay.
Does that feel okay?
Yep.
Okay. And again, either, regardless of how you're doing it, if you're getting the correct answer and I can understand what it is that you're doing, I'm not going to complain a whole lot. You know what I mean? Great. Any final questions on these homeworks 1 or 2? Okay. So let's go ahead and we're going to do 4.2 today. So in 4.2, we're going to start with a definition. Well, actually, 2 definitions. So these 2 terms that we're going to talk about here are angle of elevation and angle of depression. And I'm going to define these just as with a picture. Because really what we're going to be using this vocabulary to do is like to draw pictures from a story problem or whatever that we're going to be solving. So I'm not going to give like a word definition because it's not really very practical for what we're going to be using. So let's say we have two people. One of them's at a lower elevation, the other person's at a higher elevation. Now, each person, when they're just standing normal, are going to be looking kind of straight ahead. That's their normal kind of line of sight. And let's say the person at the bottom here looks up at the person above them. So they're raising their line of sight from parallel to the ground to that elevated position. We call this an angle of elevation, where somebody at the lower level is looking up to the person at the higher, or the thing at the higher level. And I'm abbreviating angle of elevation as AOE there. I hope that's clear. Similarly, the person at the higher elevation, if they look down, they're lowering their line of sight to see the person below them. So that would be the angle of an angle of depression. The most common mistake that students make is they try to put the angle of depression here. Remember, it's always from the line of sight to the new line of sight. So it's never going to be like inside of the triangle that we kind of form between the vertical wall and the ground and the other person. What can we say about this angle of depression, this angle of elevation, geometrically? What'd you say? You're mumbling something. They're congruent. That's correct. Why are they congruent? Do you remember the name? They're alternate interior angles. So if you have two parallel lines cut by a transversal, the line of sights for the two individuals are parallel. So if you have two parallel lines cut by a transversal, alternate interior angles are congruent, is your theorem from your geometry class. Now, I don't care a hill of beans that you remember the definition or the name of it. Just that if you can look at the picture and go, okay, I know those two things are congruent or equal or whatever, that's good enough. Okay. So that's the main piece of content here. Let's run through a couple of examples and we're going to finish up section, this section here right quick. So Christy is looking up at the Fisher Building in downtown Detroit. She is standing 200 feet from the base of the building and finds the angle of elevation to the top of the spire to measure 66 degrees. How tall is the Fisher Building? So I'm going to start by drawing a picture. So here's Christy. Here's my Fisher Building. We're going to call that the top of the spire. And it says she's looking up to this. So that's my angle of elevation. And we're 200 feet from the base. And we're going to assume that the Fisher Building is perpendicular to the ground. I think that's a fair assumption in almost all cases of buildings. The one exception might be What building do you know isn't perpendicular to the ground? Leaning Tower of Pisa. You know, that'd be the one famous exception to that rule, but almost any building that you are sure, unless you're sure it is not perpendicular to the ground, we're going to go ahead and assume that it is. That's a typical thing you'd want to do with building, right? And we're asked to figure out how tall this thing is. So there's my x. So you have a right triangle, you know, an angle and a side, and you're looking to find the length of another side. What are we going to use to do that? I can just use SOHCAHTOA, right? Relative to this angle, I know about the adjacent side, and I'm looking to find out about the opposite side. So which one of those three should I use? Sine, cosine, or tangent? Tangent. So we'll say tan 66 is equal to opposite over adjacent. I can multiply both sides by 200 to get the x by itself. And then it's calculator time. What do I have to be mindful of before I type this into my calculator? The mode. What mode should I be in to type this into my calculator? Degrees. How do I know that? The angle was measured in degrees, right? What mode do I know my calculator's in right now? Radians, because we just got done doing radian problems, so I got to make sure I switch that first. So you're starting to get into the nightmare test where you're going to have to make sure you're remembering to switch back and forth between your modes. If you get answers that make no sense, what's the likely issue going to be? You're in the wrong mode. Yeah, goofikin. So 449.2. Everybody okay with that? Not a terribly difficult problem, right? Let's do another. It says Jane has climbed a tree and is looking down on her friend Mary. Jane has climbed 17 feet in the air, and the angle of depression to Mary is 49 degrees. How far is Mary standing from the base of the tree? So there's Jane, there's Mary. We're assuming that the tree is perpendicular to the ground since it doesn't say otherwise. Jane 17 feet up in the air. Now here's the place we got to be careful. She's looking down at Mary. So this angle here is my angle of depression. Everybody's cool? So right away I can say that that angle is also 49 because of alternate interior angles. Everybody agree with that? Alternatively, you could say the other angle at J is 41. That would be okay also. But you need to get one of the angles inside of the triangle. And we're looking for this side x. Again, we're going to be using SOHCAHTOA. So relative to this angle, we know the opposite side, and we're looking for the adjacent side. So we can use tangent. So I can multiply both sides by x and then divide by tan 49. And then it's calculator time. And I got about 14.8. God bless you. Is that a sneeze? I'm not sure.
No.
Oh. Okay. It's okay. Must have been funny, whatever it was. Okay. One more example. This one is the most challenging of the three examples by quite a bit. Says Claude and Simone are riding bikes in Paris. How romantic. At one point, they look up and measure the angle of elevation to the top of the Eiffel Tower to be 32 degrees. This is exactly what I think of when I'm in a romantic bike ride in Paris. Right? When they pedal 100 meters closer to the tower, the angle of elevation changes to 37.5 degrees. How tall do they estimate the Eiffel Tower to be? Everybody's cool with the picture I've drawn here? Okay. What's the issue, though, with this picture? Do we know a side length and an angle measure for any right triangle here? No. That's a booger. So if we knew this little piece, though, we could do this problem, correct? That piece that I call y. If I knew that length, I could do this. You guys agree? So what I'm going to do is I'm going to create a system of two equations. I'm going to think about two triangles. So in the triangle with 32 degrees here, this bottom side is going to be 100 plus y. And then this other triangle has side y and x. So far, so good? The first triangle, I can say that tan 32 is equal to x over 100 plus y. In the second triangle, I can say tan 37.5 is equal to x over y. And now my goal here is going to be to solve this system. Numerically, I think the easiest thing would be to solve this system for x first, and then we're done at our answer. But if I look at this algebraically, that seems like it's going to actually be a little bit more difficult. I'm actually going to solve this for y, and then plug that answer back in to get the x, which I think is going to be actually the easiest route through this. So the first thing I'm going to do with this system is I'm going to get both of these equations equal to x, so I can just substitute them in. So if I multiply the first equation by 100 plus y, and I multiply the second equation by just y, I now have that both equations are equal to x. Is that so far so good? Since they're both equal to x, I can set them equal to each other. Be good with that. To solve this for y, then I have to get the y's on the same side of the equation. So I'm going to first distribute the tan 32 through. And then I'm going to subtract the tan 32 to the other side to get, or the y times tan 32 to the other side to get all the y's on one side. Everybody good with that? Now everything on the right-hand side has a factor of y in it. So I'm going to take a greatest common factor of y out. So now the y is in just one place instead of two places. And divide both sides by tan 37.5 minus tan 32. Calculator time here. So I'm going to use the fraction command on my calculator. So I'm going to press alpha and y equals and then choose the numerator over denominator command. So I can just type this in the way it looks on my sheet of paper. That way I don't have to monkey with a bunch of parentheses and it doesn't get so ugly. Everybody okay with what I typed in? Press enter there. So y is about 438.6. But that's not what we're looking for. Remember, we're looking for x. So what I'm going to do then is just take this equation and plug the y in to get x. So I'm going to take that answer times tan 37.5. So 336.6 meters tall. I don't really know how tall the Eiffel Tower is, but that's probably close. What do you think? Anybody been to France? About 1,000 feet tall? I don't know. Who knows? Wikipedia would, but I'm not really interested in going to find that. So that's kind of the worst case scenarios where you might end up having to solve a system. But that's not so bad. All right. And I'm going to start 4.3 here a little bit. We'll talk a little bit about 4.3, but we're not going to finish it. But I'm going to barrel ahead here a little bit today. Mostly so that hopefully by the time Friday rolls around, the asynchronous day will just be like your review day to work on stuff. Well, there's only 3 sections in chapter 4. So we're starting section 3 right now. We should finish it on Wednesday. Next week sometime. We'll figure that out on Wednesday.
Will we like have a review day?
We'll probably have a situation where like I'll take questions and then we'll start chapter 5 stuff and then take the test the following. Something like that is probably what I would do.
Okay.
Does that feel okay? Okay. So just also worth pointing out, at this point, we haven't taken a Chapter 4 homework quiz,
Right.
and we're starting the last section in Chapter 4. And Friday's an asynchronous day,
Like next class.
so you might think that would be, logic would tell you that that's probably coming sooner rather
How
than
would you
later.
feel about not putting this section on it?
4.3, I would not.
Okay, no, this is
Okay. Well, 4.3 we haven't started. 4.3 is, I think, the most difficult, will be the most difficult section for you. Okay. So one thing that we can, or one important application that we have for trigonometry is that it's going to allow us to break up complex movements into easier components. So the idea here is, say like you're here and you want to go to here. One way you can describe that is just going directly, right? Another way you might describe going from point A to point B would be, well, we go this much straight forward, and then you go that much straight up, rather than describing that path on a diagonal. Both of those two are going to result in getting the same location. But one of them is much easier to describe. You know, if you're going, okay, go straight east and then go straight north, versus cut along this section at a diagonal. Everybody's okay with that kind of idea? Both of those are describing the same ending point, or way to get to the same ending point. So when we talk about these kind of navigation problems, we're talking about things moving. Navigation has their own separate way of describing angles. I know, right? So let's start by defining that. So the course or bearing of an object is given as an angle of the object's line of travel. Here's the kicker, though. Now we're talking it going clockwise, and it starts at due north. Yuck. Why, navigators, why? So let's just start with some example here. So we're going to start with just giving you some bearings and convert these into standard position angles. So this is a bearing. So bearings start at due north, and they go clockwise so that's my alpha, right? Everybody agree with that? My standard position angle starts at the positive x-axis and goes counterclockwise. So what is theta going to equal in this case? 90 minus alpha, or 32 degrees. Everybody okay with that? Let's just do a couple more examples here. So let's say we have the bearing beta, which is 164 degrees. So again, since this is a bearing, we start at due north and we go clockwise. So here to here is 90, and then like 74 more puts us over here somewhere, right? Now our standard position angle starts at the positive x-axis and goes counterclockwise. So that's my theta, my standard position angle. What does theta have to be in this case? Well, let's see, we have 90 here, 90 there, 90 there, and then this little sliver, which is going to be how much? $16 degrees. Everybody okay with why it's 16? Okay. So that's going to be 286. 90 plus 90 plus 90 plus 16. Okay, so let's say we have another one. This is gamma, which is 221. Okay. Never eat shredded wheat. Again, we're going clockwise from due north. So 90, 180, and then like 41 more puts us here. Everybody's still doing good? Drawing our standard position angle, so 90, 180, and then it's a little bit more. So theta is going to be 90 plus this sliver. What does this sliver got to be? What do you guys think? $49, right? I'm just doing 270 minus 221. Taking the next biggest quadrant, 90, 180, 270, 360. I'm just taking the next biggest one and subtracting to get the sliver. So 90 plus 90 plus 49 is 229. Let's do one more example. Let's say delta is the bearing 299. Again, we're starting at due north and we're going 299 degrees. So 90, 180, 270, and then like 29 more. Puts us there. And then my theta, I'm actually going to put my label down there. Again, starts at the positive x-axis and goes counterclockwise. So it goes to there. So it's going to be 90 plus what? 61, right? Ooh. Alyssa?
What are all the different signs? Are those just like examples of bearings, or like?
Oh, they're the symbol that I'm using to represent
Yeah.
them. So I'm just using different Greek letters.
Okay.
So they're just, might as well be like letters A, B, C, D.
Okay. Yeah.
You know, just alpha, beta, gamma, delta. Those are the first 4 Greek letters in the alphabet. So I just use them for a little bit of enrichment. So it's like you've seen some of these other symbols before, so you're not like freaked out when you see it.
Yeah.
It's just like a variable name. Could be, I could draw a slice of pizza. You could use foods for our variables. Pizza, taco, spaghetti, you know, chicken leg, whatever. They're just names. This feels like a good place to stop because I don't think I can do the example problem inside of 10 minutes going slowly through it. So we'll stop here.